Golang has a new package called Secret Mode, and we really need to talk about it. The gist of the feature is straightforward. You can now run code in secret mode, and after the function finishes, it immediately erases the registers and stack it used. Then, heap allocations made by the function are erased as soon as the garbage collector decides they are no longer reachable. This might not sound like much at first, but features like these ones are a great chance to review some important software concepts we don't run into on a daily basis. After all, coding is not all about centering buttons on a screen or performing basic database operations on the server. And here is the first lesson most of us don't really think about when programming in these high-level languages. Memory is not ephemeral just because your function returned. In other words, just because your function is done doesn't mean the data it handled is gone. It might still be sitting around in memory, on the stack or heap, waiting to be overwritten. If you processed something sensitive like a password, a cryptographic key, or a secret token, there's a real risk it could be leaked later, either through a bug, a memory dump, or a side-channel attack. In computer security, there are known attacks which exploit this exact behavior. For example, cold boot attacks can recover encryption keys from memory minutes after shutdown simply because that data wasn't properly cleared. A much more popular example is the Heartbleed OpenSSL vulnerability that lets attackers read arbitrary chunks of memory, often revealing private keys and session tokens. So, while most of us don't have to think about this kind of stuff in our day-to-day life, having a good understanding of basic concepts across all software layers is what separates good software developers from the rest of the pack in this new era of artificially generated code. As I was saying in a previous video, one of the most important skills to have in the near future is to cut through the bullshit and remove the unnecessary complexity generated by AI. And you'll be able to do this only if you have a clear mental model of how software actually works. Back to the video, Go's new secret feature will protect you from 3 categories of attacks. First, passive memory exposure is the most common and honestly the most boring one since it involves plain old memory dumps, crash logs, or debug tools that expose raw memory. If your app crashes and someone inspects the process memory, whatever was on the stack, or worse, on the heap, might still be sitting there in plain text. Secret mode reduces that window by actively zeroing memory after sensitive code runs. Forensic recovery is more exotic but very real. Cold boot attacks are the classic example here. Remember that RAM doesn't instantly forget everything when you shut down a machine, so if someone has physical access, they can reboot into a custom OS or move the RAM to another device and dump what's left. Finally, side-channel leaks are a bit trickier. Instead of reading memory directly, attackers try to infer secrets by measuring timing, power usage, cache behavior, and even electromagnetic emissions. It's how researchers have extracted encryption keys from air-gapped systems and why modern CPUs have so many mitigation layers for speculative execution vulnerabilities like Spectre and Meltdown. And this is actually a very interesting piece of trivia about how computers work at a very low level.
Awesome trivia! In 10 seconds!
Some CPUs are basically cheating to stay fast. They do this thing called speculative execution, where they try to guess what instructions you'll need next and start running them before they're actually allowed to. This makes things faster if their guess is correct. If it isn't, that computation is simply discarded. But while the results of a mispredicted computation are discarded, the microarchitectural side effects are not. Caches get warmed, branch predictors get trained, and memory access patterns change. So, attackers realized they could deliberately trigger speculative execution on code paths that access secret data, then measure those side effects afterwards. The secret is inferred by timing how fast certain memory locations respond. Fast means it was cached. Cached means it was touched. Touched means the secret influenced execution. This really puts things into perspective when you realize what others are doing while we waste our time in retrospective Teams meetings. Back to the video, secret mode doesn't magically fix speculative execution issues, but it does tighten the places where secrets can linger long after you've used them. And that matters because most modern exploits target systems at their weakest boundary. Data being left unguarded because nobody bothered to clean up after themselves is one of those situations. But what's really interesting is that this is a bigger shift than it looks. Go, for most of its life, treated memory safety as a correctness problem, not an exposure problem. Of course, we got bounce checks, race detectors, and garbage collectors, but all this protects stability. Secret mode, on the other hand, protects confidentiality. That's a different category of responsibility. In practice, this reduces the attack surface in 3 ways. It narrows the lifetime of sensitive values, it ensures the cleanup is actually executed even under compiler optimizations, and it integrates the behavior with the garbage collector so heap-based secrets don't outlive their purpose. Quick side note, this compiler optimization point is actually one of the most subtle security traps. In high-level languages, if you manually write code to zero out a secret, the compiler might notice that you never read the variable again after you zeroed it, so it can decide that the cleanup is unnecessary and simply deletes the zeroing instruction. This optimization, while great for performance, can actually become a massive security vulnerability. If you enjoyed my rambling about software topics, you should check out one of these videos next. Please don't forget to violently smash all the buttons YouTube is throwing at you these days, and until next time, thank you for watching.